If you recall from statics, we learned the rigid body equilibrium conditions, that if this rigid body is subjected to multiple external forces and couple moments, for this rigid body to be in equilibrium, the conditions must be satisfied that the resultant external forces acting on this rigid body must be zero in the vector form, and the resultant moment of all the external forces and couple moments summarized about an arbitrary point P must be zero as well. Again, this equation is also in vector form. For a 2D problem, the equilibrium conditions reduced to 3 scalar equations. Normally, these 3, although you can write alternative equations, that resultant force along the x direction equals to 0, resultant force along the y direction equals to 0, and again, the resultant moment summarized about any arbitrary point P equals to 0. Now, based on these 3 scalar equilibrium equations, we're going to write the equations for motion in a similar format. For a rigid body with a given free body diagram, if it is undergoing general plane motion, then we can draw its equivalent kinetic diagram with linear acceleration AgX and Ag(y) at its gravitational center G, and the angular acceleration alpha for this entire rigid body. And we can write a system of 3 scalar equations in a similar form as the equations for equilibrium as we talked about earlier. In this set of equations, resultant force along the x direction equals to m, the mass of this rigid body, times the x component of the linear acceleration at its gravitational center. Resultant force along the y direction equals to mass times linear acceleration along the y direction. Resultant moment summarized about any arbitrary point P equals to this term right here, which is known as a kinetic moment about point P. But what is it? Remember, we talked about before that the term ma, mass times acceleration, can be considered as an inertia force. Similarly, Ig alpha, Ig being the mass moment of inertia of this rigid body about an axis that passes through the mass center point G and is perpendicular to this xy plane, and alpha again is the angular acceleration. This term Ig alpha can also be considered as an inertia couple moment, and therefore this term right here, kinetic moment about point P, can be considered as the resultant moment about point P caused by the moments of ma plus the free couple moment Ig alpha. In this expression, dx and dy are the moment arms of these two ma terms, and the positive sign and the negative sign again correspond to either counterclockwise rotation or clockwise rotation. Since in this set of equations, the resultant moment is calculated about any arbitrary point P, then for convenience, why don't we summarize the resultant moment about the gravitational center point G? This way, the two inertia force terms magx and magy both pass through point G, therefore they do not create any moment about point G. Therefore, the resultant moment about point G simply equals to the term Ig alpha. If the rigid body is undergoing translation, which means that the body is not rotating about any axis, therefore, the rotation term Ig alpha disappears from the kinetic diagram. Therefore, in the equation of resultant moment about point P, the kinetic moment about point P only includes the moment caused by the two inertia forces magx and magy. Or, once again, if the resultant moment is summarized about point G, the mass center of this rigid body, then the resultant moment simply equals to 0. Let's look at this problem. We have a toy cart with total mass of 0.2 kilogram. Its center of gravity is marked on the image. It is subjected to a 0.8 Newton horizontal force pulling it to the left. And we need to determine the acceleration of the cart as well as the normal forces acting on the pair of wheels at point A and point B. Since we can assume that the wheels are free to roll and have negligible mass, therefore, this is a problem of translation, and every point belonging to the system moves with the same linear acceleration. We start this problem with a free body diagram of this toy cart with unknown forces and A and MB, the normal forces at the two wheels, and the weight force which can be determined. And from observation, we can tell that this toy cart is going to move horizontally to the left. Therefore, this is its kinetic diagram showing only linear acceleration AGX pointing to the left. So we set up our coordinate system, and now we are ready to write our three equations of motion. First, resultant force along the x direction equals to m, the mass, times AGX, the linear acceleration along the x direction. And since we only have one horizontal force, the 0.8 Newton applied force, therefore, from this equation, we can solve for our linear acceleration. And then, from observation, there is no motion along the y direction, therefore, the resultant force along the y direction equals to 0, and that includes our two unknown normal forces and the weight force. For our third equation, we can summarize the total moment about any arbitrary point, but for convenience, we're going to summarize the total moment about point G, the center of gravity, because for translation, the resultant moment about point G equals to 0 since there is no angular acceleration alpha. Therefore, we can write this equation out. Based on the last two equations, we can solve for the two unknowns, NA and MB, simultaneously. And this completes this problem, but let's also try an alternative approach. We write the first two equations the same way, but for our third equation, instead of summarizing the moment about point G, the center of gravity, we're going to summarize the moment about point A, and that equals to the total kinetic moment about point A, which is calculated in this case as the moment caused by the inertia force mAgx, which at this point has already been solved. The advantage is, this way, the resultant moment about point A does not include the unknown force NA, since NA has line of action passing through point A. Therefore, in this equation, as you can see, we only have one unknown, which is MB, and we can solve for MB directly from this equation. Then we substitute MB into the second equation, and we can solve for NA. And we get exactly the same results as the previous approach. So it is up to you to decide what approach you'd like to use. Let's quickly look at this example involving dry friction. We have a uniform 100-pound crate with dimensions shown, and the coefficient of kinetic friction between the crate and the surface is 0.2. And an 80-pound force is applied on this crate, and we need to determine the linear acceleration of this crate. Let's start with the free body diagram of this crate. The center of gravity is right there in the middle because the crate is uniform. We mark the weight force as well as the unknown normal force and frictional force on this free body diagram. If you remember from statics, this point A, the location where the normal force is applied, right now is unknown. Let's assume it is at a location of x from the center of gravity. From statics, we learned that through equilibrium, if x is calculated to be 1.5 feet or above 1.5 feet, that means that point A is right there at the corner, and that indicates the crate is going to be tipping over. For now, let's assume tipping over does not occur, but sliding does. Therefore, the kinetic diagram of this crate is very simple, since the crate is undergoing translation only. And also, since sliding occurs, the kinetic frictional force simply equals to mu kn, in this case 0.2 n. Therefore, now we are ready to write our three equations of motion. Resultant force along the x direction equals to mag. There's no motion along the y direction, therefore resultant force along the y direction equals to 0. And since this is translation, the resultant moment about point G is also 0. And we notice that we have enough equations to solve for all of our unknowns: the frictional force F, Fr, the normal force N, the linear acceleration ag, and the location x. We're going to solve for x first. X equals to 1.2 feet, which is smaller than 1.5 feet. And this indicates our original assumption is correct. Sliding occurs, tipping over does not. Therefore, we can now solve for our linear acceleration, and that's the answer to this problem.